Okay, guys, I think we can start today's session. So, I don't know, like you have attended yesterday's session. We have started with the simulation of the R2D2 robot, and like the URDF creation, we are doing the simulation in a step-by-step manner. Okay, so I'm actually following the official tutorials of ROS for URDF creation and also for simulation. Okay, so we are basically using two main packages. I think you already familiar with the URDF sim tutorial, which is having the URDF, okay, step by step URDF for simulation, and the tutorial URDF tutorial GitHub. So this is having the step by step tutorial of the URDF creation, okay, basically the sacro creation. So after creating the sacro, we are switching into this tutorial. Okay, so this tutorial is giving an idea how to create a simulation based on the URDF that we have created. Okay, so yesterday we have discussed two URDF. Okay, that is 09's publish joined and 10th, yeah, 10th first transmission. It's like, I mean, each sacro file is having incremental changes. Okay, and the final sacro file that is using for the simulation is the 30 diff drive.urdf. So they actually did this for understanding, like in each stages what is actually happening. Okay, so in the 09 sacro, what happened was we have taken the last sacro file that we have designed in the URDF tutorial. Okay, that is this one. Okay, so we have taken the 08 urdf.sacro we have taken, and then added something to this, I mean the same sacro, which is the gazebo ROS control plugin. Okay, so this plugin is very important to connect the URDF with the gazebo, okay, and ROS. Okay, so we have added that in the first sacro. Then in the second sacro, we have introduced a new concept called transmission tags in sacro. Okay, so basically while designing the URDF, we are writing the relationship between joins and links. Okay, but if we want to control these joins in simulation or in hardware, we have to attach an actuator or a motor to these joints, right? So the transmission tag actually specify what kind of actuator or what kind of gear ratio that we are using for this robot or for that specific joint. So the transmission tag is an additional tag that we are using in URDF. So if you simply search for URDF tags, you will get this transmission tag as well. So in the list you can able to see the transmission. So if you click it, the entire concept and all the things inside the transmission tag you can able to see. Okay, so in the transmission tag we are giving the actuator name. I mean, you can give any name like the joint, and we are using a symbol transmission, which is one of the transmission implemented in ROS. Okay, so there is a thing called transmission interface. Maybe I can. So how the transmission is doing, so that is actually in this package called transmission interface. So the transmission interface is actually for like sending the position, velocity or effort, whatever it is, and it is connecting to the controllers. So yesterday I have mentioned a diagram. I think you have seen this diagram. Okay, so the communication between the Gazebo plugin, that is a Gazebo ROS control, to the hardware interface, okay, which is again a layer, okay, that is actually acting between the robot and the controllers. Okay, so on the right side you can see the hardware, on the left side you can see the Gazebo, and the robot hardware interface is actually acting as the bridge between the controllers and the simulation or the real hardware. Okay, so in order to work with the simulation and the robot hardware interface, we need to add Gazebo ROS control plugin. Okay, that is acting as a bridge between URDF and the hardware interface layer. Okay, so for Gazebo we are using robot HW sim hardware interface. In real hardware we are using hardware interface robot HW. Okay, yeah, so these things I think we have discussed yesterday, and yeah, so in the 10th sacro they have added a single transmission tag for the head, okay, head rotation. Okay, I think we have tested that. So if you enter the transmission for a specific joint, then only you can connect to the controller and you can able to move that joint in Gazebo. So maybe I can just show you the last thing that we have done. Just a second, I think there is a question. Okay, what about now? Okay, now it's correct. Okay, so let me start with the 10th one, which is the last thing that we have discussed. So according to each progress in the URDF or sacro file, you can also see the progress in the launch file. Okay, so in the first launch file we have seen how to start the joint state controller. So from this diagram, from this diagram you can able to see we have to load controllers for interacting with the joints. So the controllers is basically a PID loop. Okay, so we have to attach a ROS controller to the joints in the robot, and there is a joint state controller, joint state publisher controller, which is basically sending the joint state of each joints. Okay, and rest of the controllers are for moving position. It can be any type of controller, position controller or velocity controller or effort controller or torque based control. Okay, so in the first launch file we have seen how to start the joint state controller. Okay, so joint state controller will be like reading the state of each joints. Okay, and in the second launch file we have seen we are starting the joint state controller as well as the head controller. Okay, so if you remember, we have seen the configuration of the head controller. So the controllers, ROS controllers, I think I have shown you the package ROS control. It's a very important package which is having a list of controllers like position controller or effort controller, trajectory controller. So you can simply reuse these kind of controllers. Okay, so this is the diagram. I think this is the same diagram. Like there is a control manager in ROS and you can add a controller, and the controller is for controlling a joint, right? So in between there is a bridge or there is a layer, an abstraction layer. It's called hardware interface. So that hardware interface is acting as a bridge for reading and writing from the joint. Okay, reading the joint state and writing the joint values. Okay, so you can load any number of controllers. Controllers are like plugins. Okay, so if you want to load like 8 controller for 8 joints, that is quite possible. Okay, and you can load controllers using this simple step. Actually, if you want to load a join position controller, you can simply mention the controller configuration in a YAML file. Okay, by the way, just want to know the controller, the list of controller that is already available. I can show you just a second. So these are the list of controllers that is available in ROS now. So you can find differential drive controller, effort controller, position controller. So if you take the position controller and if you take the XML file, okay, so I mentioned that these all are plugins. So you can find join position controller, join group position controller. Okay, for controlling a group of joins with position value, you can use the join group position controller. So what we are doing is these all are available. Okay, these all are available. So you can simply mention the type of the controller that we are using and the joint that we want to attach. Okay, and what we are doing is we are simply loading these controller configuration. Okay, so you can actually write this configuration in a single YAML file, or you can write the configuration in a separate YAML file. Okay, and then give a namespace. Okay, just give a namespace and yeah, so if you load these controllers, it will be actually showing in that namespace. Maybe I can show you, maybe I can just launch this file that is 10head dot launch. So URF sim tutorial and the 10head dot launch. Oh, okay, so I'm just loading.
Sir, is there a way to view XML format on the screen?
Which XML format?
Sir, if we are given a URDF file,
Yeah.
Then there is a, yesterday I saw there was an option to make it as an XML view.
XML tree.
So XML view, so like for example, this launch file, we can view it as an XML format. So it is showing all the tags and aligned. And
yeah, so this is actually viewing in XML format only. Like you can check it's properly colored. I mean, in gedit, if you just go to the view and in the highlight mode, if you just give XML, then it will be viewing as XML.
got it, sir.
Okay, but we will be using Visual Studio also. So in Visual Studio, we can visualize the URDF, and also we can make changes in the URDF, and that will be updated in the Visual Studio. So after discussing the basic stuff, I will be like explaining that. Okay, so I just started the simulation, and so if you check the ROS param, okay, ROS param list, you can able to see there is R2D2 head controller joined, R2D2 head controller type. Okay, so this parameter is actually coming from this one. Okay, is coming from this this line, and there is R2D2 join state controller. So here, okay, join state controller, R2D2 join state controller published rate. So this is for this controller. Okay, So basically what we have done was we have actually loaded uh, two controller parameters with different namespace. Namespace is what? This thing. Okay, so R2D2 join state controller slash publish rate. R2D2 join state controller type is for publishing the join state of the robot, and this is for controlling the head joint of the robot. Okay, so now we can able to see the parameter is loaded. Okay, these two lines actually loading the parameters, and this node, okay, this is the controller spawner node or controller manager. Okay, so these nodes are already, these packages are already available. Okay, so you don't need to like install, or you don't need to do anything. You can simply mention it, and what this node does is that it is actually starting these type of controller from these parameters. So it is starting the joint state controller, it is starting the head controller. Okay, and so currently we can able to control the head joint in the from the simulation. Okay, so how to control, I think I already mentioned that yesterday, but I can show you. So if you do a ROS topic list, you can able to see a controller head controller command topic. Okay, that is actually the topic for controlling the joint. Okay, so when you publish some topic to this topic, when you publish some values to this topic, then what happening is that it will be the joint will be moving. So you can see the head actually moved. Okay, head actually moved. So just a second. Okay, and if you give 0.2, see, right? So what we are doing is we are literally controlling a joint in a robot. Currently it is from the simulation, but if you connect the actual robot and set these controllers and set the robot hardware interface, and if you can able to communicate with the hardware interface, like this diagram. So in this diagram you can see the hardware interface is the abstract layer. Okay, so encoders are actually sending the joint state value, and the hardware interface is giving the values to the actuators, real actuators. Okay, so if you do that, then you can move the robot in real. Okay, the real robot will move like this. So by sending a topic, you can able to move the joint. Okay, and so that is what we have seen in the 10th head dot launch, and the 12th one is actually somewhat, I think they have added some more controllers. They have added the joint state is already there, head is there, and now they have added the gripper. Okay, they have added the gripper.yml. so the gripper what is a YML file? Gripper.yml. So let's see what is inside the gripper.yml file. So it is having a join group position controller. Oh, sorry. Okay, because gripper is a combination of 3 joins, right? So what join group position controller does is that you can send the position values to 3 of these joints simultaneously. Okay, you can send the value to these 3 joints simultaneously. Okay, so what are the joints? Left gripper, right gripper, gripper extension. Okay, so this configuration will load what? This configuration will load the gripper controllers. Okay, and the namespace is gripper controller, R2D2 gripper controller. Got it? So let me start the 12th one. Just a second. Yes, it is loading. Okay. Yes. So now you can able to see the head actually came because we have assigned a controller in the head. Okay, that's why we are getting the join state. Okay, so the join state controller will be I mean retrieving the joint values if we assign a controller to it. Okay, so now what we are doing is we are checking the topics. So here you can see the gripper controller command is here, okay, as a topic. So ROS topic pub. So it's difficult to publish actually because it's an array, I guess. Let's see. Yeah, it's a float 64 multi-array. So let me see. Just a second. I think we have to give like an array. So maybe 0.2, 0.1, 0.3, something like that. Yeah. I think it's not the field data must have a float value. Let me check. Just a second. Float 64. Oh, just a second. Multi-array ROS topic pub. Yeah, I just want to know the syntax. Yeah, I think it's the same. Oh, okay. Okay, so there is a data. Okay, this configuration actually worked. So let me try. Okay. So we have data. That is what we need to put the values. So 0.1, then 0.2, 0.3, something. Yeah, I think that work. So here you can able to see the gripper actually opens. I mean, I just push some random values, by the way. Okay. So I'm just giving 0.3 or something. Yeah, you can see one gripper actually moved slightly. And if I'm giving 0.1 or something, oh, there is no change. Maybe I can put minus 0.1. Yeah, so the first value is actually for the extension of the gripper assembly, and if you provide 0, okay, so 0 is the, I think, yeah, the default value, and you can simply change the values of the gripper. Okay, so we are giving these values simultaneously, 3 values simultaneously, and we can able to control the gripper assembly, and you can test it simply by using this syntax. Okay, so just use this ROS topic pub command to test check the joins. Okay, yes, so that is what the 12 gripper dot launch. Okay, so if you check the URDF, you can able to see the transmission tag is assigned to the gripper. Okay, so there is a transmission tag for gripper extension, and transmission tag is for the gripper joints. There are 2 gripper joints, so left gripper transmission and right gripper transmission. It is actually inside a sacro or a macro, inside a macro. Okay, so they have assigned the transmission, then only this will work. Okay, and finally we have the 13 differential drive URDF. Okay, so far we have made the head worked. Okay, head was working, and the gripper assembly is working. We can able to control, and finally what's left is the wheels, right? So wheels, we can actually independently control these wheels. We can able to do, but what we really need is we need to control by giving a linear and angular velocity to the robot. Okay, if you give the velocity commands to the robot, then the robot should rotate its wheels based on the linear and angular velocity. Okay, so basically we need to control the wheels in a way that it should work in a differential drive manner. Okay, so the wheels should obey the differential drive manner. We are not controlling independently, we are controlling by a differential drive controller. Okay, so for moving the robot in a differential drive behavior, we need another controller. So if you just check, just a second, if you check the ROS controller, you can able to find the differential drive controller. Okay, so this controller, so what is this controller? Controller for a differential drive mobile base. Okay, so if you have a mobile base which is having differential drive wheel assembly, it can be 2 wheels or 4 wheels. Okay, working like the speed of the robot, or the direction of the robot is actually controlling by adjusting the speed of individual motors. Okay, so this is what we are using in the last sacro file. So in last sacro file, we can see there is a transmission tag for all the wheels. Okay, all the wheels, there is a transmission tag. Okay, so that is actually inside a macro. So you can able to find when I launch it, just a second, when I launch the 13 differential drive, basically we are launching all the controllers. Okay, so you can able to see the gazebo is here, then RVs, there is no error, we are getting the transformation of all joint. Okay, and you can also able to see one more TF, which is odom. Okay, odom. So I'm just putting the fixed frame of RVs as odom. Okay, I'm putting odom, and yeah. So what was happened when we started? We can just go to the launch file, 13 differential drive, and if you just visualized this launch file, you can able to see we are loading the differential drive configuration. Okay, we are loading differential drive configuration, the configuration for loading the differential drive controller, and here is the configuration. Okay, here is the configuration. So you can see the type of the controller is diff drive / diff drive controller, and we have the publish rate at 50, and then we can mention which are the left wheel and which are the right wheel. So if you have multiple wheels, you can mention in an array. Okay, so you can mention in an array, so left wheel and right wheel you can mention, And also these all are other parameters of this differential drive controller, because for the differential drive controller to work, it should require the separation of the wheels, the distance between the left and right wheels. That is this, like if you check these length, no, the right and left wheel, the distance between these two wheels are the wheel separation. Okay, so that need to mention. And also post covariance, these all are related to the odometry, I will explain. And what is the base frame of the robot? So for our robot, the base frame is the base link, right? So we have to mention that. And then if you have any limits for the velocity and acceleration, you can mention that. Okay, so what this controller does is that it will subscribe to the command velocity from the user. Okay, so if you feed or if you publish a command velocity to that topic, then what will happen is that the robot will move, and also it will compute the odometry of the robot. Okay, so for example, if you give a command velocity to the robot, the controller will compute the odometry, okay, of the robot, because the controller can able to get the encoder reading or the joint states from the gazebo. Okay, so that based on that joint state, it can compute the odometry and it will publish that odometry. Okay, odometry means the local estimate of the robot position. Local estimate means from the starting point of the robot, where is the robot? Okay, maybe it's x direction, maybe 1 meter from the starting point, and y will be like 0.5, and the theta, the orientation will be another. So yeah, so these are the parameters that we have to mention. Okay, and it's all these parameters are loaded in the differential drive namespace, and we are simply loading the differential drive controller. Okay, and in order to publish the command velocity, so if you check, maybe I can show you. So if you just check the ROS topic list, you can able to see these topics from the differential drive controller, which is command velocity, then odometry. Okay, so these are the important topics. That is the odometry is publishing by the controller, and command velocity is subscribing by the controller. So if you just do ROS topic echo odom, you can able to see the current pose of the robot. Currently, I think we just yeah, we didn't move, but these all are very small values. Okay, these all are very small values. We can equate to 0. Okay, and the command velocity is what we are providing with this RQT plugin. Okay, so you can start this RQT plugin. This is what it is mentioning. Like here you can see we are loading the RQT plugin. Okay, so when you give a linear velocity, you can see the x value is increasing, x and y. I mean, you can check it. Okay, so this if we provide fixed frame as odom, so odom start from here, from the starting point, and you can see the odom value, odom transform. With respect to the odom, the base link is here. Okay, and you can see the odom value is changing. Okay, robot odom value is changing, and if you check the odom value, the y is actually nearly 0. Okay, it's a very less value. The x value you can see is 3.5. No, so each block, each unit is 1 meter. So 1, 2, 3, 4. Now it's between 4 to 5 odometry. You can see 4.4. Got it? So the command velocity is publishing by the RQT plugin. So you can see the command velocity is publishing by the RQT. It's constantly publishing. Okay, And if you want to rotate the robot, simply give the angular velocity, and now you can able to see it's rotating. Okay, and now if you look the orientation value is changing. The x is actually almost same, the orientation, which is actually in quaternion. Okay, so we can't able to like understand the value, but you may have to convert the quaternion into Euler angle. Okay, so this is what this differential drive controller gives to us. Okay, so from the R2D2 simulation, what we essentially did was we actually seen how to use a differential drive controller for our robot. So the differential drive controller can be used for both simulation and for the real robot. Okay, so the same simulation will work with simulation and the hardware. Only thing is, if you want to connect with the hardware, then we have to configure this one, the hardware interface, and also the encoders should publish the joint state, and like this hardware interface things should be done. Okay, so I can give you example how to do that. Okay, so this is what this example basically does. Like, it actually showing the usage of what the differential drive controller robot, differential drive controller, position controller, and joint state controller. Okay, so this is the example, and this is available. You can check it from the official GitHub repository. You can check it, and maybe I can give you 5 minutes for asking questions related to the R2D2 robot, and after that we can switch to um, uh, this tutorial. Just a second. Just a sec. Okay, so it's a time for Q&A. Okay, after this we can start with another example, a basic robotic arm. Okay, so that we can check it after the Q&A. Yeah, so after this example we will be seeing the current robot simulations like Husky, Turtlebot. Then there are many simulation example, but the fundamentals are the same. Okay, so so let me know if you have any questions, guys. I know it's not very easy. Okay, I know, but you have to like practice. Okay, you have to practice, and then only you can understand these things. It will take some time anyway. Okay, so after this we are going to see this. Okay, we are going to see these examples. Yeah, so let me know if you have any question, guys. Any questions? Okay, maybe I can switch to the RR board. Okay, RR board is a robotic arm. It's a very simple robotic arm. So what I'm doing is I'm just taking these packages. These are a set of packages. So I'm just cloning it into our workspace. Okay. So I'm just opening the terminal and then git clone. Okay, I have done the cloning. Then I'm doing the catkin make. Okay, just a second. Okay, so there is some issues. Okay. Yeah, there are some issues actually. It is not compatible with the the latest ROS packages. Maybe let me check for Noitic.
Sir, I'm not able to see the
Oh,
screen.
okay. Just a second. I think it's, yeah. Can you able to see now? Okay,
Yes, sir.
okay. Let me try. Let me try to set these packages. Seems like it is not compatible with the hmm. Here's RR board description. Let me check. Okay. So this was the original repository. RR board description control, RR board gazebo. Okay. So let me try another repository. Okay. Just taking it. I'm just deleting the package that I have cloned. Just cloning this repository. And checking it. So it is having an entire workspace. So we don't need it. We just need these two packages. Just copy into SRC and deleting this. And then we are making or building this workspace. Yeah, it seems working. Let me just switch into the RR board description. Okay, yeah, it is switching. And let me check the RR board control. Okay, that is okay. Then I'm trying to launch something from the description. Let me check any use. Okay, gazebo.launch. Yeah, I think it's loaded. So on the top, I think there, yeah, I can understand. Okay. Now I'm starting the controllers. ROS launch RR board control. RR board control. Okay. Oh. Okay. A lot of messages coming. Okay. Oh, okay. Got it. Let me close one thing. So here you can able to see a robot with two joints, a robotic arm, very basic robotic arm, and it is also having the simulation of a laser scanner and a camera. Okay, so that is actually the interesting thing. So if you want to simulate an expensive LiDAR on the simulation, you can easily do it. Okay, so that is advantage of doing simulation. We don't need to buy the sensor, but you can able to simulate it and get the data and write the software. Okay, so here is the fully working simulation of RR board. And okay, let me use maybe I can install one package. I can explain that. EZ RQT EZ publisher. So I'm actually going to install a plugin in RQT. So this plugin, no, this plugin is very user friendly to publish value to the controller topic. So later we have used ROS topic pub and all, right? But if we can use the EZ publisher, we can able to control the joins via GUI. Okay. So let me see. Let me install it, and we have the robot ready. And let's see how to control the join. So in the meantime, I can list out the topics from the controllers. So we can able to see the join position controller command, then join to position controller command. So these are the two joins, okay, and we can control these joins by sending values to this topic. And we can also see the join state. Then there is an image from the camera simulation, camera sensor, and there is a scan as well from the laser. Okay, and this RVIS, no, RVIS is having the visualization of all this stuff, I think. Let me increase. Okay, so I'm just putting a block and I'm just scaling up. Okay, so I'm just copy pasting the same thing here. Okay, so the laser could able to detect, right? The laser is not penetrating the objects. So now if you check the RVIS, you can able to see these objects detected. Okay, so these are the laser scan. Okay, that is detected the objects. Okay, now yeah, I mean I'm just showing the output. I didn't explain anything. I just show the output. So now let's control these joints using the EC message publisher. Okay, so this is a very convenient plugin called EZ publisher. So simply take that topic, which is this, and then you will get a slider. Okay, now just move the slider and you can able to see that joint. Okay, that joint is actually moving. We don't need to publish manually, but we are like moving through a slider. So the same can be applied for the joint position 2. So here the position 2 is actually, maybe I can show you like this. Okay, see, the second joint is actually moving. Okay, and the second joint is having the sensors. That is, there are two sensors. One is camera and one is laser. Okay, so I can show you one thing. So on the right side there is a simulation, and on the left side we have the visualization from the sensors. Okay, so these sensors, no, these sensors are ROS plugins. Okay, so what it does is that it will simulate a laser in the simulation, and it will give these values as a ROS topic. Okay, so if I'm just increasing 2.1, okay, so here on the left side bottom you can see the camera values, I mean camera view. So if you change the join values, you can see the laser scan and also the camera visualization is actually changing. Okay, okay, like the real robot. I mean, this is what happening in a real robot, right? Okay, so this is a very basic robotic arm, 2-DOF robotic arm, and with some sensors on it. Okay, and for the R2D2 also we can put the same sensors. If you want to make it autonomous, you can put a laser scan on it, then you can able to do SLAM, G mapping and all. Okay, so that is our project topic. Okay, so I will be discussing about the autonomous robot simulation, and you can work on these two topics for the project. Okay, so these two, I mean, the job opportunities and also the research opportunities are mainly in navigation. So in navigation, there is a SLAM, a localization, then the perception also, deep learning, all this stuff. So there are a lot of opportunities in navigation, and this is manipulation. Okay, the pick and place and all that is also having, but mostly I have seen a lot of job opportunities and research opportunities in the self-driving cars, robotic, I mean AGV, I mean warehouse robot, all these things. Okay, yeah. So this was the simulation, and this was the output actually. And let's see, maybe we can just go through the two packages very quickly, and then we can conclude. So if you check the URDF, you can see there is a RRBot Sacro. Inside that, they are actually mentioning the links and joins. Okay, the same thing that we have seen, there is no difference. And in the Sacro, you can find they have included this much of Sacros. Okay, so this Sacro, no, this RRBot dot Sacro will be including this much of Sacros. Okay, so they are doing in a very modular way. So you can see other Sacros from this folder. So there is RRBot properties. So these are some variables that we are using inside the main Sacro file. And when you modularize, make sure the name of the robot should be the same. So here the name of the robot is RRBot, here also RRBot. Okay, and they have separated the gazebo parameters, like these are the friction parameters, and these are the plugins that we are using inside the gazebo. Plugins means plugins for like the main gazebo plugin, there is a gazebo ROS plugin, and they also mention the transmission tags. Okay, there are two joints, right? So the transmission tags for that. So we are using effort joint interface. You can change it. Okay, and also this is the sensor definition, like for the laser scan, and this is for the camera. Okay, so I will explain that. And they are also starting the joint state publisher, but that is not very required, I will say. Yeah, yeah, I will get back to that. And yeah, this is the color, like you have seen the robot is having orange and black color, so that is actually achieving through this. And these are some macros that we are using for inertial parameters. Okay, inertial parameters, and these are some materials, some colors. Okay, so yes, so these are the important stuff that RRBot is having. Okay, and where is the controller then? Controller, where is the controller? So the controller is actually putting in another package. So basically the configuration of the controller is this. We need the joint state controller, we need a joint position controller, and joint position controller again. Okay, but it is from the effort controllers. I mean, you can use the position controller from effort controller or position controller, anything. And you can also mention the PID values. Okay, also mention the joint. And here we are giving a namespace. This is actually the namespace. So under RRBot namespace, there are three controllers: joint state controller. So this thing, no, this thing is just a name. Okay, this is actually the thing. Okay, so this is the actual controller name. This should not be I mean, we can't write any name. This thing you can write. This thing also you can write. These things, these names. But this should be the exactly the same. Otherwise, it will show error. So while launching the RR board control.launch, what is happening is that it is launching Gazebo, okay, with all these plugins, that is differential drive plugin, and I mean not differential drive, position controller, and the sensors, everything. And here it is loading the controllers, and here it is starting the joint state publisher, and here it is starting the visualizer. Okay, so these all are the things that is happening in this simulation. Okay, so what you can do is you can simply go through this repository. Maybe I can share this repository for reference. I will be also including in our source code. So just go through it, and rest of the things that I think we can discuss next week. So I am planning to take some more classes, guys, next week for I mean for doing the projects. So mainly I'm focusing on to this chapter, that is autonomous mobile robot, how to create an autonomous mobile robot, like how to do mapping, navigation stack, all this stuff. Okay, but we didn't discuss much about the navigation stack and all, but planning to like create simulation projects for autonomous I mean with autonomous mobile robot and robotic arms. Okay, so that is what I'm thinking about the projects. Okay, and I can give you some references, and I can give you some lectures. Okay, and then I can guide you for the project. Okay, so maybe after next week my availability will be less, but I will be online, and you can put your doubt on Discord, and I can support whenever I get time. So yeah, so let me know if you have any confusion for RR board. Maybe next class also I can give you more idea about RR board control and description. Now if you have any questions, I know we didn't discuss about the sensors and all, but maybe next class we will do that. Let me know if you have any questions regarding the RR board description, I mean the simulation and all. Any questions? Maybe I can start the simulation again, just check it, and let me know if you have any questions. So we have so it is having a fixed joint on the world frame, and world frame is actually the fixed fixed frame. Then link 1, link 2, and link 3, and this is the laser. Okay, on the top you can see the laser scan. It's a 360-degree laser scan, and this corresponding to this box corresponding to a camera. Okay, so these all are separate links. Okay, these all are links, and so the sensor I think I can explain in the next session. I will announce the next session. So please cooperate with me. Like next week, I think maybe after 9 o'clock or 10 o'clock we can do 1 hour session or something. Okay. Okay, so if you don't have any doubt, we can conclude for today. So just have a look on to the RR board. Yeah, go on, Kalpesh.
Sir, joint is prismatic
No,
joint,
no.
correct?
It's actually the articulated joint only. So maybe I can take the RR board. Prismatic is actually linear movement. So if you have, yeah,
This one is
it's a
revolution.
revolute joint. So you can able to see in the RR board sacro file. So here are the links of the camera that I will explain. So if you just check, there are, here they are putting as a continuous join. I mean, basically it's revolute. Okay, for robotic arm it's actually revolute, but for this demo they actually made it continuous means you can, I mean, rotate 360-degree. Okay, but for robotic arm it's revolute only. So the we can set a limit. Okay, so here you can see it can work like, maybe we can put the values actually in radians. So 3.14, 3.14. So I think we can able to rotate, see. Okay, so basically, I mean, we can change to revolute, and if the joint is revolute, then there is a provision to put the limits. Okay, yes, see, it is actually like working very realistically. Like if you just move, it is actually not stopping immediately. There is a PID value, right? So that is what it is, having some inertia. Okay, and you can change this PID value of these controllers. Yeah, yes, yeah,
Yes, sir.
yeah. Okay, so if that is clear, I will announce the class date. We will have Friday and Saturday sessions, and in between I need to take some more classes for the project. Okay, so it will be after like 9 p.m. Okay, okay guys, so we can conclude for today. Thanks for attending. So I will be updating the notes soon. Okay, so see you next week. Okay, bye everyone.